Hello, welcome to our talk. My name is Hyoung. Along with my colleague Zichen, I'm going to present about bloom filter overhead in LSM-Trees using the cost model that we have developed and how to reduce this overhead. This work is a collaboration with Aneesh, Raman, and our supervisor Manos Athanassoulis. The log structured merge tree is the core data structure of several key value engines like RocksDB, LevelDB, and many more. And they are widely used because they can balance the read and ingestion performance. Before we jump into the details, let's see the breakdown of an LSM read query. There are three main components: bloom filter, data access, and other costs. As we move to fast storage devices from SSD to feature NVM, the time spent on data access decreases. For NVM, the lookup time is mostly spent on bloom filters. The time spent on bloom filters dominates for fast storage devices. Let's see more details why this happens and how we can reduce this overhead. To support fast writes, LSM-Tree stores all inserts in a memory buffer. When the buffer is full, it flushes the buffer to storage as an immutable sorted one. In order to balance the read performance and ingestion rate, LSM-Trees maintain these sorted ones in multiple levels. Depending on the compaction policy, there can be only one run per level or multiple ones, but the size of each level grows exponentially by size ratio. To enhance the lookup performance, the commercial system employ metadata such as bloom filters and fence pointers. Bloom filters can identify whether the target key belongs to a given level or not, so it can screen out the keys that have no possibility of matching. Fence pointers are the min-max ranges for each disk page, and they ensure that the at most one I/O occurs within a single one. A point lookup first checks the in-memory buffer and then traverses a tree from the shallowest to the deepest level until it finds the first match. For each level, bloom filter is always looked up first. If the query result is negative, then the lookup moves to next level. If the query result is positive, the lookup needs to access data. However, bloom filters can have false positives, so if it fails to find the matching key, the lookup proceeds to next level. When there is a matching key, the lookup finishes. Here, we need to take a note that the bloom filter is always queried in all levels before finding a match. Then, what is the cost of querying a bloom filter? We model this using TH, TP, TD, and alpha. TH is hashing time, TP is the probing time, TD is the data access time, and alpha is the fraction of empty queries. To query a bloom filter, we need to calculate k hash indexes and check the bits indicated by those hash indexes. If there are any bits with value 0, then it is negative. If all bits are set, then it is positive. For negative result, the lookup finishes, but for positive results, the data should be accessed. Positive results can be true or false, so the data access comes from two parts: false positives in empty lookups and the non-empty lookups. Ideally, bloom filters use k-independent hash function to obtain the minimal error rate. But it is not practical because hashing is a CPU-intensive task. So, in order to save CPU overhead, multiple indexes are calculated using a single hash function and cheaper bitwise operations. As shown in this example from RocksDB, the hashing cost can be reduced by a vector of k. However, is there any side effect? We conducted a benchmark to see the impact of this hash sharing within a bloom filter. Here, we vary the bits per key and measure the first positive rate. As you can see, both schemes using k-hash functions and hash sharing show the first positive rate close to the theoretical expectation. Here, for various key sizes, the lookup latency is shown. The hash sharing can reduce the lookup latency by a vector of k. So far, we have discussed the cost of using bloom filters. Then what is the lookup cost in LSM-Trees? LSM-Trees can have leveling or tiering as their compaction policies. Depending on the compaction policy, the number of runs per level is different. Leveling allows only one run per level, while tiering can have 3 runs per level. The lookup should be performed per run, thus the leveling can provide better read performance. Let's start from lookup cost in level LSM-Tree. First, we model the lookup cost in a single level. All lookups can be either empty or non-empty. The lookup cost in a level is the sum of these costs for empty and non-empty. And using this lookup cost per level, the total lookup cost in level LSM-Tree can be derived. As you can see, the lookup cost consists of 3 parts: Bloom filter cost, data access due to false positives, and data access for non-empty lookups. Bloom filter query cost is proportional to the number of levels in a tree. Thus, the hashing cost accumulates as the number of levels in a tree grows. And non-empty lookups cause data accesses, so hashing is more prominent for empty queries. Using Bloom filters are particularly beneficial when there is a large gap between Bloom filter and data access. What will happen when we move to faster storage devices? The future MVM is expected to have access latency around only 250 nanoseconds. On the other hand, the murmur hash takes 235 nanoseconds for a 1 kilobyte key, which is 10% faster than MVM. So this leads us to question, what is the time spent on hashing as we move to faster storage devices? This graph shows the fraction of hashing within lookups in various devices as we vary the empty ratio. For SSD, hashing is not dominant even for all empty lookups. However, as we move to fast storage devices, the hashing is getting more dominant. Here, where the 6% of lookups are empty, the hashing is around 5% for SSD. However, in MVM, over 90% of times is spent on hashing. Similarly, we can get the lookup cost in tiered LSM-Tree. However, it has to go over more Bloom filters. The hashing overhead is more severe for tiering. As you can see in this graph, hashing dominates the lookup cost than leveling. Then how we can reduce this hashing overhead in LSM-Trees without harming the performance?
To solve the above problem, we propose hash sharing as follows to reduce the CPU overhead. Now we focus on the leveled LSM trees. As shown in the left-hand side figure, when a GET request is being processed in the LSM tree, it has to iterate every level until it finds the key. Within each level it has iterated, it has to calculate the hash function and probe the Bloom filter, as you can see in the middle figure. Therefore, the same hash function is calculated multiple times, which brings CPU overhead. In fact, as shown in the right-hand side figure, we can reuse the single hash digest to avoid expensive hash calculations. To quantify how much gain that can be achieved by hash sharing, we combine the cost model with the speed numbers that we've mentioned above, including hash calculations, storage device accessing. In this figure, the x-axis represents different storage devices, while the y-axis represents the estimated gain. The gain increases from negligible for hard disk drives, 1% for solid-state drives, to 6% for PCIe SSD, and it is projected to up to 40% for non-volatile memory. In other words, the gain increases rapidly with faster storage devices. In the evaluation phase, we built an LSM-Tree prototype system using RocksDB's fast local Bloom filter. The experiment procedure goes as follows. We populate the LSM-Tree in advance and measure 1 million point lookups, report the average latency of 5 experiments, and we use PCIe SSD with direct I/O by default. There are also some other default parameters. we will fix the entry size as 1 kilobyte or 2 kilobyte. Use the data volume as 22 gigabytes. Unless otherwise specified, we will always use uniform and empty query workload. As for LSM tuning, we will set the file size to 2 megabytes, size ratio to 10, and bits per key set as 10. In the first experiment, we examine the impact of the key size. Since the time spent on hash function is dependent on the key size. In this experiment, we fix the entry size as 2 kilobyte so that we can vary the key size from 32 to 1 kilobyte, as you can see from the x-axis. The left-hand side y-axis represents the latency per lookup, which corresponds to the bar chart, while the right-hand side y-axis represents the gain, which is corresponding to blue curve. The solid bar represents the time spent on Bloom filters, including hashing and probing, while the rest of two bars represent the data accessing and the time for other operations, something like binary search in fence pointers. As we can observe, as key size grows, the difference between two adjacent solid bars increases, while the other two bars remains nearly the same. As a result, as key size grows, the gain increases up to 20%. It is worth mentioning that for skewed query workload, the gain increases up to 60%. Here we generate a deep VM query workload. Since many frequently queried keys are blocked by the Bloom filters, the data access hardly occurs, and that is the case when the hash calculation can dominate the query performance, and thus the gain is higher. In the next experiment, we vary the data size. Here we reduce the size ratio to 2 so that we can have more levels. As you can see from the x-axis, the number of levels ranges from 8 to 14. According to the blue curve, the gain initially increases as the number of levels grows, and then plateaus. In fact, this is consistent with our cost model. You can find more detailed explanations in our paper. Next, we conduct our experiment on different storage devices, including SSD and PCIe SSD with and without direct I/O. We also emulate non-volatile memory using Randex. Note that without direct I/O, many pages are cached by the system, and that is the reason why SSD and PCIe SSD without direct I/O can achieve similar performance to RAM disk. When the accessing speed is comparable to hash calculation, the time spent on hash calculation can dominate the query performance. And thus, hash sharing leads to higher gain for faster storage devices. Next, we examine the impact of the I/O cost of empty queries. Here, the red curve represents the gain for RAM disk, while the blue curve represents the gain for PCIe SSD device with direct I/O. In this experiment, we vary the bits per key short as BPK. Smaller bits per key indicate higher FPR and thus higher I/O cost of the empty queries. Observed from the blue curve, for slow storage, high I/O cost of empty queries leads to smaller gain. However, for fast storage, the gain does not depend much on the cost of empty queries. In a word, fast storage leads to high gain. Even for slow storage, if the cost of empty queries is low, that is low FPR, we can still have high gain. In our last experiment, we varied the empty lookup ratio alpha. As you can see from the x-axis, we varied the alpha from 0 to 1. And according to the experiment on PCIe SSD, the gain on PCIe SSD increases up to 20% as alpha increases. When it comes to a RAM disk, the benefit is pronounced and the gain is increasing to around 40%. It is worth mentioning that when it comes to a RAM disk, we still have 10% gain even if all queries are existing queries. That is the case when alpha equals 0. Overall, hash sharing has more impact for faster devices, which is exacerbated for empty lookups. To sum up, in this work, we observe Bloom filters dominate LSM-Tree query performance for fast storage. Second, we develop a query cost model to quantify and predict the amount of time spent on hashing and data accessing. Finally, we reduce hashing by sharing it across Bloom filters and levels, leading to performance up to 40%. And it is worth mentioning that when it comes to a tiered layout of LSM-Tree, we have higher gain using hash sharing. And thanks for attention. We are glad to take any questions from you. Here, the GitHub link is our repo for hash sharing.